All right, day 4 of our sequences and series unit. Today we're going to be talking about geometric sequences and series, or rather, we're going to be using geometric sequences and series to answer a few varying word problems involving a couple different situations, different scenarios. So today's lesson is just going to be going through your homework for tonight. So, homework 4 is uploaded on our website. You need to grab that and work through those problems. And if you get stuck, there's an answer key online, and you can also watch this video. Or maybe you are stuck, and that's why you're watching this video. But if you hadn't tried it yet, don't watch this video until you've at least tried it. Because you gotta make some sense of this for yourself. If you get stuck, come here. And here we go. First problem is what you should have tried for homework the previous night, but we're going to go through it now here. We're going to make some sense of all these different pieces. So again, you are interviewing for a job and receive 2 offers. $20,000 to start with guaranteed annual increase of 6% for the first 5 years. And that's where I'm going to stop reading for now because I want to make sense of this. We're going to be talking about a sequence of numbers. Our sequence is going to represent each year's annual income. So our first term in this sequence is going to be 20,000, the amount we make on year 1. So that's going to be A sub 1, which is year 1's salary. Then what is year 2's salary going to be? Well, year 2's salary is going to be that original $20,000 plus a 6% increase. So I'm going to maintain the $20,000, but I'm going to add to that 6% of that $20,000 because I'm increasing by 6%. So I'm going to be adding 6% of that $20,000. I'm only doing this to show a point that was confusing some people, so I want to clear that up here. Notice we have 2 terms here. 20,000 is our first term, and 20,000 times 0.06 is our second term. Both of these terms have that 20,000 in common, which means I can factor that 20,000 out of those terms. And what will I be left with? Well, I'll be left with, in that first term, if I factor 20,000 out of 20,000, I'm left with 1. In the second term, if I factor the 20,000 out, I'm left with just that 0.06. And we can simplify that now to 20,000 times 1.06 to get our second term. That is why our constant ratio R here has to be 1.06. It can't just be 0.06. Because if it was just 0.06, all I would end up with is that bit, 20,000 times 0.06, which would be a much, much smaller number than 20,000. That would only be 6% of 20,000. But we don't want 6% of 20,000. We want 106% of 20,000 because it's a 6% increase on top of the 20,000 we're already getting. So our common ratio R has to be 1.06. So that's the starting point for this problem. That's what we need to understand. So we have our first term, 20,000. We have our common ratio R is 1.06. So now we can write our explicit formula. A sub n equals the starting term, 20,000, times our common ratio, 1.06, raised to the power of n minus 1. And that is for option A right there. But we also have option B right here, where we are starting with $22,000 and we are increasing by 3% each year, so our ratio there would be 1.03. And then now we have our 2 explicit formulas, and now we can talk about these 2 different problems. So, the first question says, which offers best if your goal is to be making as much as possible after 5 years? Option 2, which is best if your goal is to make as much money as possible over the contract, 5 years? Now, I interpret question 1 as saying, which offer will give you the highest salary after 5 years? Question 2, which offer will make you the most money over 5 years? Now, if we want to know the highest salary over 5 years, I interpret that as what is your salary on the 6th year? So, if we want to know a salary, that is asking us for a term in the sequence. So we can use our explicit formula. A sub n, where n is 6, because we want the salary on the 6th year, because it is after 5 years. So A sub 6 equals our starting amount, our starting salary, 20,000, times 1.06 raised to the power of 6 minus 1. And so when you crunch that number, you should get 26,764.51. And remember, we're talking about dollars here. And what would this number represent? This number is your salary on year 6, because we're after 5 years, so year 6. Now let's compare that to the salary you'd make on year 6 with the other offer. So A sub 6 for option B is our 22,000 times 1.03 to the power of 6 minus 1. And that offer will get you a salary of 25,504.03 on your 6th year. And so option A is going to be the better option if you want to be having the highest salary after 5 years. But what about if you want to make the most money as possible over the 5 years? Well, let's look at which option is better then. So now we're saying we're looking at a summation, our total amount of money accumulated over those 5 years. So now we want the 5th partial sum, which, using our formula for the sum of a geometric series that we came up with in the previous lesson, we have our starting amount, 20,000, times 1 minus our ratio, 1.06, raised to the power of n, which is 5. Notice n in this problem is 5 because we want the sum of the 5 years. N was 6 in the last problem because we wanted the salary after 5 years. So here we go. Divide that by 1 minus your common ratio. Crunch that in your calculator to find how much money you've made over those 5 years. When you type that in, you should find that over the 5 years, you've made $112,741.86 if you went with option A. But what about option B? For option B, we're looking again at the sum of the 5 years, but now our starting value is 22,000 times 1 minus 1.03 to the power of 5 over 1 minus 1.03, and now we can crunch that number. With option B, you've made $116,800.99 over the 5 years. So that is the better option if all you want to do is make the most cumulative money over the 5 years. Which is the better option? Which should you choose? Well, I think it depends on your goal. You're probably going to have to renegotiate that contract after 5 years. If you know it's going to expire after 5 years, then maybe go with option B because you get the most total money. But, well, if you think you're going to continue working with that company after 5 years and they're going to increase your salary by a % based on your previous salary, then maybe it's better to go with option A because you'll get more money from that % increase since you had the higher salary on year 6. Well, either way, the option is yours to choose, but here's the math that will support your decision. And now let's look at the next problem. This question is very similar to the last one. We have a couple different offers here, different scenarios, and we want to figure out which one is going to be the best option for us. So we've just signed a 7-year professional football league contract with a beginning salary of $2 million per year. Management gives you the following options with regard to your salary over the 7 years. Option 1, a bonus of $100,000 each year on top of your yearly salary of $2 million. Option 2, an annual increase of 4.5% per year beginning after year 1. An annual increase of $95,000 per year beginning after year 1. Which option provides the most money over the 7-year period, which the least, and which would you choose? Okay, well, now first off, a lot of people are having trouble distinguishing the difference between option 1 and option 3, other than clearly the $5,000 difference in those dollar signs there. Well, option 1 is not saying that your salary will increase on a yearly basis. It's saying that each year you just get a one-time bonus of $100,000, which means on year 1 you will make $2,100,000. On year 2 you will still make $2,100,000. You're not going to make $2,200,000. Your bonus isn't increasing. It's the same $100,000 bonus on top of your same $2 million salary each year. And so, if we want to know how much we've made over the 7 years, all we need to take is the salary, the $2 million, plus the $100,000 bonus that you're guaranteed every year to get $2,100,000 each year for 7 years. Just multiply it by 7 to get your answer. Which will give you a total of $14,700,000 if you choose option 1. All right, well, what about option 2? Option 2 is saying an annual increase of 4.5% beginning after year 1. And that's another place people were confused. They're like, well, why does it say beginning after year 1? Well, let's write our geometric explicit formula for this and then understand the situation and make sure that it will work for us. So, if we're writing our explicit formula, a sub n will equal our starting quantity, which is 2 million, times our common ratio, which should be 1.045 for a 4.5% increase, raised to the power of n minus 1. That is the model that we've come up with, and let's make sure that it makes sense here. If I plug in 1 for my first year, I should get a salary of $2 million. Do I? Well, yeah, I do, because you plug in 1 to the exponent. 1 minus 1 is 0. So 1.045 to the 0th power is 1, so I get $2 million. And then when I plug in 2 for year 2, I get 2 minus 1 is 1, so I get the 1.045 multiplier on top of my $2 million. So my increase has started after year 1. So yes, this model does work, which means I can use my summation formula to find the sum of 7 years, which will equal my starting amount, 2 million, times this fraction, 1 minus my ratio, which is 1.045, raised to the power of the number of terms, which is 7 years, divided by 1 minus my ratio, 1.045. Calculate that number, and with this option, we're going to get $16,038,303.58. So clearly option 2 is significantly better than option 1. You get over, well, almost, I can't talk, I can't do math. You get a little less than $1.5 million more, which is pretty awesome. Now, important distinction here. The reason I wrote my explicit formula first, a sub n, is to ensure that our model would work for this with the n minus 1 exponent. If my exponent did not say n minus 1, I would not be able to use the summation formula in the same way that I just did. I would have to tweak it. So when you're going through this, if you don't have that exponent of n minus 1, you're going to be in trouble, and you're not going to be able to use that summation formula in the same way. So make sure if you're using the formula in the way that we've come up with it, that you do in fact have the same explicit formula there with the first term ratio to the power of n minus 1. We did, so we're good. And now let's do this last problem, option 3. Make this one dark purple. So going back to the issue, what's the difference between option 1 and option 3? Well, option 3 is saying we are increasing our yearly salary each year. Each year after the first, we're increasing our salary by $95,000. If we're increasing by a constant amount each time, we're talking about an arithmetic sequence. So a sub n equals our starting amount, which is still 2 million, plus our common difference, which is 95,000 times n minus 1. It fits our model, so we can use our summation formula. Again, it makes sense with that after year 1 thing, because our starting year will be 2 million, and then it'll be 2,095,000. So we can use our summation for the first 7 years, Gauss's formula, our 7, number of terms divided by 2, times the first term, which is 2 million, plus our last term, which we need to find. And so we need to figure out what is a sub 7. Well, that's going to be 2 million plus 95,000 times 7 minus 1, which is $2,570,000. That's how much you'll make your last year there. So $2,570,000 there. What is that sum? And with that option, you're going to make $15,995,000 over those contract years. And so, looking then at these 3 options, The geometric option, option 2, with the percentage increase each year, is going to be the best option if you want to make the most money. The bonus of $100,000 each year will get you the least amount of money. And then the arithmetic option, the $95,000 increase after the first year, it's going to get you pretty close, but it's in the middle. It's about $40,000 less than the geometric option. Now, which option would I choose? Well, I would choose the second option because that's always going to make you the more cumulative amount of money. But in addition to that, that's going to make you more money each year as well, other than the first year. On year 2, you're going to make almost $90,000 more. On year 3, you're going to make $183,000 more. On year 4, you're going to make $282,000 more. Year 5, $384. Year 6, $491. And on that 7th year, you're going to make $603,000 more than the other option, which is nuts. You absolutely, absolutely should choose that option. Okay, so let's move on to the next question. Balls drop from a height of 30 feet. Each time it strikes the ground, it bounces up to 0.8 of the original height. So 80% of the original height with each subsequent bounce. So question A says, what height will the ball bounce up to after it strikes the ground for the third time? So think about after it strikes for the first time, it has reached a height of 24. After it strikes the second time, it has reached a height of 19.2. So this third strike right here, the easiest way to calculate that is just to think about this recursively. Take strike 2 and multiply it by the common ratio. So if you think about that in terms of the sequence, let's say a sub 3 equals a sub 2 times your common ratio r. And so a sub 3 is going to equal our second term in the sequence, which is 19.2, times our common ratio, which is 0.8. So figure out what that is by multiplying those two numbers together. And you find that the height after the third bounce is 15.36, and we're talking about feet here. Now, if you've noticed, I've been writing this actually in terms of the sequence number, which is important here, and it's going to help us with the next part. I have defined my third sequence is the height after the third bounce. There's a sub 3. My second term was the height after the second bounce, and my first term was the height after the first bounce, which means if this is my sequence where a sub n equals the height after the bounce, and then n equals the bounce number, it means that this first number here, 30, isn't part of my sequence. So if I go to part B, how high will it bounce after it strikes the ground for the nth time? Well, B is saying write an explicit formula here, but my formula has to be a sub n equals my first term, which is not 30. It's 24, and I know a lot of you want to write 30 for that first term, but it doesn't really fit the scheme here because when it has a height of 30, it has not yet hit the ground. And so my first term is 24, actually, and then my common ratio r is 0.8 because each time it reaches 80% of its previous height, raised to the power of n minus 1, we have our explicit formula. So now question C says, how many times does the ball need to strike the ground before it bounces less than 6 inches? Alright, well, how are we going to do that? Well, first off, notice that it's asking a question about inches, and all of our terms are in terms of feet. And so instead of 6 inches, I'm going to use half of 1 foot, because there are 6 inches in every foot. That's a total lie. There are 12 inches in every foot, which is why 6 is half of a foot. 6 inches, half of a foot. Okay, that was a really long explanation explaining that a ruler has 12 inches on it, and halfway is 6. Whatever, we're there. Who cares? So what do we want? We want to know how many times does the ball need to strike before its bounce is less than 6 inches. Well, imagine if we wanted to let that bounce equal exactly 6 inches. And then we could use our explicit formula from the previous part of this question. and solve for n. That's how I'm going to approach this problem. So let's divide 6 by 24. 6 divided by 24 is 1/4. So we have 1/4 equals 0.8 to the power of n minus 1. And we're going to have to use logs again. So log of base 0.8 with the argument 1/4 equals n minus 1. So again, change the base formula. Log of 1/4 divided by log of 0.8 equals n minus 1. Either way, you know what's funny? I just made that whole big deal about how we needed to use 1/2 instead of 6 inches, and then I totally didn't do that. So let's back all of this up because that is all totally useless to us. We don't want 6 there, we have to have 1/2. My bad, y'all. That was me being silly. So starting over, 1/2 is what we're setting our sequence equal to because we're saying how many number of bounces would it take to get us to an exact height of 6 inches, which is 1/2 of a foot. Well, now we can divide by 24 to get 1/48 equals 0.8 to the power of n minus 1. And now we can rewrite it as a log by saying the log, still with base 0.8, of the argument 1/48 equals equals n minus 1. So I'm going to add 1 to both sides now and say that plus 1 equals n. So crunch that number. And when you do so, you get this ugly decimal 18.348, which doesn't totally make sense to us because we're talking about number of bounces, and you can't have 18.348 bounces. But remember, we're saying that would get us exactly 6 inches, but we're never going to have a bounce height of exactly 6 inches, essentially what this is telling us. So now we need to think about what should our answer be. Well, should it be 17 bounces? Should it be 18 bounces? Or should it be 19 bounces? Well, think about what our sequence is doing. The terms of our sequence are getting less and less and less. So if the bounce of 18.3 is getting us exactly to that height of 6 inches, then if we had not bounced that far, so 17 or 18, then we would still be too high. We'd still be bouncing higher than 6 inches, because not until that 18.3 will it actually be low enough to be right at 6 inches, which means if we want to be less than 6 inches, we need to use 19 bounces for our number of bounces. And if you plug that into your calculator, a sub 19 equals 24 times 0.8 to the 19 minus 1. You'll see that you get a height of roughly 0.4 feet, which means we are less than half a foot. And if you do the same thing but use 18 for the number of bounces instead of 19, you'll get a height of 0.54, which means you are still above 6 inches. And so our answer has to be the 19th bounce will get us below 6 inches. So now, the last question here, what total distance does the ball travel before it stops bouncing? Well, that is actually dealing with an infinite sum here. If you picture that ball going down like that, picture this kind of curving down like that, that's our situation here, and you don't yet know how to do infinite sums, but we can kind of trick our calculators into answering this anyway. Let's do a summation of just a really large number of bounces. If by the 20th bounce we're already, at about the 19th bounce we know we're already at 0.4, and we're just going down to the ground, it's not going to take that many more bounces, but let's just say, let's find the 50th sum right there. Doing so, we're going to take the first term in the sequence. First term in the sequence, remember, is 24. So it's going to be 24 times 1 minus our ratio, which is 0.8, raised to the power of 50, the number of bounces, divided by 1 minus 0.8. And let's crunch that number real quick and see what we get. Okay, and that actually gets me a really ugly number, so I'm going to be a little more extreme, because if we're approximating an infinite sum, 50 is clearly not close to infinity. So I'm going to double that and say, let's go with 100 bounces there and see what happens. And again, on our next class, we won't have to be crafty like this. We'll be able to actually calculate it. But when you plug in an n value of 100 to, say, 100 bounces, then we get the sum of 120 feet, which gives us some confidence because it's an integer, and we always feel happy when we find integers as answers. But is that actually our answer? No, it can't be our answer, because think about what we got going on here. Every single time this ball bounces, it is going up and back down. So for every single height that we generate in our sequence, it's doing double that. From the first term of our sequence, 24, we're actually going 48. From the second term in our sequence, 19.2, we're actually going double 19.2. So for all of these terms in our sequence, we're actually doubling it. So we need to actually take double whatever that sum was for all of those heights, but then we also have that original height of 30 that it traveled down. And so we need to add that 30 to it to get the actual distance traveled for answer D right there. So we need to double the 120, and we need to add 30 to it. And when we do so, we get 270 feet for the total distance traveled by that ball up and down as it continued to bounce over and over again. Now again, next class, we will know how to do this with a little more solid numbers rather than just approximating what this should be by plugging in a large n value. But this gets us there for now. Alright, this next question should be pretty straightforward after the stuff we've already done. Suppose you've just been hired at an annual salary of $18,000. So first term is $18,000. And you expect to receive an annual increase of 5%. So our common ratio is going to be 1.05. What will your salary be when you begin your 5th year? So A sub n equals our first term, 18,000, times our ratio, 1.05 to the power of n minus 1. And again, make sure that this makes sense for our sequence. Make sure the exponent n minus 1 makes sense. If you plug in 1 for the salary you get on your first year, well, you get 18,000, which is good. If you plug in n equals 2, you get 18,000 times 1.05, which represents the 5% increase from year 1 to year 2. So we're good. All we need to do is plug in 5 to get the salary on the 5th year. So A sub 5 will equal 18,000 times 1.05 to the 5 minus 1 is 4. And our term value then, our salary on the 5th year, is $21,879.11. Alright, last problem. Look at the figure below. What fraction of the square is eventually shaded if the indicated shading process continues indefinitely? So, we need to think of this as an infinite sum, and we need to think of each term in this infinite sequence as each progressing square, and whatever fraction of the whole that square is. So for example, that is A sub 1. And then this square right here would be A sub 2. And then this little tiny square right there would be A sub 3. And then this little tiny square, A sub 4, etc., 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 forever, forever, forever. So we're talking about fractions here. We want to know what fraction of the square. Well, that fraction of the square right there is 1/4 of the total square. So we know that our first term, A sub 1, is going to be 1/4 of that total square. What about the second one? Well, notice the second one is 1/4 of the 1/4 square, which is telling us that our common ratio here is 1/4. And so our sequence of numbers here, A sub n, is going to equal our first term, which is 1/4, times our common ratio, which also happens to be 1/4, to the power of n minus 1. And so if we wanted to calculate this sum, we could say that the sum, let's just pretend like we were doing this for 1,000 terms, because that would get us like pretty gosh darn close. Well, imagine if we were doing this for 1,000 terms, we would have S sub 1,000 equals our first term, which is 1/4, times this fraction, 1 minus my common ratio, which is 1/4, to the power of 1,000, divided by 1 minus my common ratio of 1/4. And now, without knowing about infinite series yet, we're going to be able to answer this question. So, think about this numerator right here. And more specifically, think about that bit right there, 1/4 to the power of 1,000. Well, that's the same as saying 1/4 to the power of 1,000. 1/4 to the power of 1,000 is essentially 0, because 4 to the power of 1,000 is a ridiculously huge number, so 1/4 to the 1,000th is basically 0. And imagine if we plugged in an even bigger number, since we're really talking about an infinite limit. Imagine if it was 1 billion. 1/4 to the 1 billion is even closer to 0. So essentially, this whole term right there goes to 0 and goes away and doesn't affect this. So really what we have is just this, 1/4 times this expression, 1 divided by 1 minus 1/4. And let's simplify this some further. What is 1 minus 1/4? Well, 1 minus 1/4 is 3/4. So we have 1/4 times 1 divided by 3/4. And then we continue to simplify this. 1/4 times 1 divided by 3/4 is saying the reciprocal of 3/4, which is 4/3. And what happens? Boom, your 4's cancel, and you get 1/3. And so, 1/3 of this square is ultimately shaded if you continue this shading process forever, which is, I think, really cool. And we can actually think about this in another way. For the moment, ignore any of that stuff right there. Ignore all of that mess right there. Don't pay attention to it. Pretend like that green square doesn't exist. Well, what fraction of the thing that remains is shaded? Well, we have 2 squares not shaded and 1 that is shaded, so 1/3 is shaded. Okay, and now let's ignore the stuff we just accounted for, and now let's focus on this next little bit where we ignore the next chunk and focus on what's there. Well, here we have a not shaded, and a shaded. So again, we have 1/3 of that remaining bit is shaded. And let's do the same thing now. Ignore what we just accounted for, and look at the next thing, ignoring the next little bit. Well, now we have a not shaded, and a shaded. Again, 1/3 is shaded. This process is going to continue on forever, which should logically make us understand why 1/3 is the amount that's shaded. And we'll get there in the next class.